Hi everybody, I'm Partha from Microchip Technology. I'm going to present today a specific application of RISC-V processor that we have been working on over Microchip's PolarFire system on chip. All right, so we start with few general understanding that like any other field, RISC-V is entering, it has already entered the marketing, the networking field because of the RISC-V's modularity and openness, and there is a lot of demand for having an open network. So we know the advantages of RISC-V. It has over the proprietary instruction set architectures, and this aids in the co-designing the hardware and the software. We understand the importance of supporting the open source networking stacks, and there is a momentum in the community for the same. And then, of course, there is cost effectiveness. All in all, from one side, RISC-V is enabling the flexible instruction set architecture, but when we think of at a solution level, we want to make it more modular and more scalable and more open. So that is what RISC-V is enabling. So moving on to the specifics of the current application, GPON, it stands for Gigabit Passive Optical Network. Many of us would know here. It is an extension of the router and the gateway framework that is there in our homes and in the residential apartments and the buildings. So basically, if you see the diagram, it consists of an OLT box called the Optical Line Terminal, and then there are endpoints, the optical network units or the optical network terminals. This technology is based on the ITU-T 984 standards. It's the fiber optics. So on the left side, you will have the Ethernet connecting to the OLT, and then you will have splitters in between, and then you can have certain, the signals multiplied to the multiple ONUs, 8, 16, 32, 64, and it goes on. GPON provides a high-speed point-to-multipoint connectivity, and each subscriber will be one ONT unit. And the downstream, that is from the OLT to the ONUs or the ONTs, is 2.5 gig, whereas the upstream is 1.25 gig. Yeah, and we have it applicable in our homes and residential gateways. So why PolarFire SoC? Microchip's PolarFire SoC family offers an industry-leading power efficiency, thermal performance, and defense-grade security for intelligent connected systems. So the security and the thermal efficiency is deeply ingrained into the PolarFire SoC. You can see that there are certain RISC-V blocks in the diagram on the orange part. So the left side is the primary core that we have, that is the E51 core, and on the right side, there are actually multiple cores. It's a quad core, U54 cores. The PolarFire SoC is divided into two major subsystems. So the topmost part is the microprocessor subsystem, or the MSS. That is where the RISC-V cores reside. And the bottom part, the middle part, is the FPGA fabric that we have. So the highlights of PolarFire SoC is that it is RISC-V 64-bit CPU complex. It is low power. It has deterministic performance, and then it has DDR, I/O, and security features. So coming to the application of PolarFire SoC to this particular solution, the RISC-V takes care of the control plane processing, whereas the flexible FPGA fabric takes care of the data path. We'll see more in the coming slides. So we built the PolarFire SoC as a GPON OLT device in the current application. So this solution is a multi-dimensional scalable GPON OLT solution that is developed. It is multi-dimensional scalable because it can be scaled to multiple copies. We can have multiple copies of the OLT MAC IP. And then we can have multiple copies of this SoC also in a final board for a final solution. There are other ways also this solution is scalable, as we will see. So just going over through the diagram, you can see that the bottommost part, we have the OLT MAC IP, which is part of the fabric that you saw in the previous slide. The upper blue portion is the MSS, which contains the RISC-V codes, and the green areas are the software running on the RISC-V. The software consists of the Microchip GPON software development kit, SDK, and just a quick overview of the basic components we have: PLOM, OMCI, and DBA. The PLOM, or the physical layer OEM, takes care of the configuration and control of the OLT device. The OMCI takes care of the management part, and the DBA is the dynamic bandwidth allocation. So we will have multiple ONU devices or the ONT devices connected to this OLT, and each will ask for some bandwidth allocation. So that's what the dynamic bandwidth allocation algorithm will decide. So yeah, we have the SDK and the MAC IP. The SDK is running on the RISC-V and it's taking care of the control plane, while the MAC IP is taking care of the data plane. So the key technical enablers for the solution, where the entire stuff is open source, the IP is in the IP catalog, while the software becomes part of the Linux for Microchip, that is again open source. The RISC-V CPU performance comes into picture for the control plane workloads. We'll look into it in a bit more detail in the coming slides. And the FPGA comes for the packet processing offloads. So the security and trust is deeply inbuilt into the PolarFire SoC. So when it comes to performance of this solution, the key considerations are that we need to meet a downstream speed from OLT to the ONTs of 2.5 gig and an upstream speed of 1.25 gig. So it is possible that in the real deployment, certain ONUs can become dysfunctional, or there's some issue power for which they need to be restarted. So there should be a minimum threshold time within which the ONTs can get restarted. It can be variable, but we have just kept it 3 minutes for our case. The DBA needs to allocate bandwidth to the respective ONUs, so that's the DBA cycle time. It keeps getting some statistics and some information on how much bandwidth each ONU will require. So based on that, the DBA decides, and it has to be typically 1,000 cycles per second. The MSS and the FPGA, the interaction between the MSS, that is the blue part, and the yellow part, so that happens to the AXI bus, and that has a specific threshold. But in the current solution, it is expected that if we connect, let's say, 32 ONUs, then it should be within 100 megabytes per second. So during the evaluations, we found that we are able to achieve the expected downstream and the upstream bandwidth. The data path recovery time is taking well within a minute. We have right now tried with 8 ONUs, and it's expected that it will meet the threshold time of 3 minutes when we do it with 32 ONUs. So one of the challenging areas that we faced is that the DBA is taking 200 cycles per second right now. We want to scale it up, and we have certain optimizations in plan. And as we increase the number of ONUs, then we also increase the number of cycles per second. We have estimated and also measured to a certain extent that the maximum bandwidth that will be required for the interactions between the MSs and the fabric, it would be 10 megabytes per second. DBA comes into picture here as well when it is having the multiple cycles, as well as there is something called as the DBRU information that comes back from each of the ONUs. And there is management and control information as well, which keeps getting exchanged per second. So moving on to even the higher layers of abstraction. So we thought of integrating VOLTHA. VOLTHA is virtual OLT hardware abstraction. It's an open source platform, and it is right now under the Linux Foundation Broadband Initiative within the Linux Foundation ecosystem. So it is said as the open source PON control, but it's more of a management, the higher layer abstraction on top of the SDK, as we'll see in a moment. The abstraction of PON solutions, allowing service providers to manage different OLTs and ONUs through a unified stack. So the VOLTHA can run on the x86 and ARM, but we thought of boarding it on the RISC-V, okay, and it will integrate the SDN controllers, the software-defined networking controllers like the Open Network Operating System. And it enables the disaggregated access networks. It decouples the hardware and the software. Quickly looking into the diagram on the right side, so we can see it's a traditional OLT device. It's a white box OLT, and it has the Open OLT agent. So whatever we see in orange is the VOLTHA. The blue ones, the top one is the Open Network Operating System. It's a software-defined networking. Software-defined networking is a framework through which we can control multiple devices, multiple endpoints with an ease. So the entire VOLTHA diagram, this is a more simplified version, consists of the VOLTHA agent that is part of the OLT device. And then there are modules for the OLT management and the ONU management. We have a core layer, and we have certain APIs complying with the standard of OpenFlow. And then that gels with the SDN controller and the applications. So the end use case with VOLTHA will look like, on top of the GPON SDK, we'll now have the VOLTHA, entire VOLTHA layer, and then we can have the servers or the application on the top. The remote client will now manage the multiple ONUs with the OLT using the VOLTHA layer. The key components are the SDK, the VOLTHA, the application servers, and the remote client. So what VOLTHA is doing is that it is turning a base GPON solution into a disaggregated software-defined and multi-vendor ready network. So we can have ONUs from different vendors which can plug on to this same OLT device. And then as a subscriber, the subscriber will first have the onboarding, and then the service activation, and then the traffic flow will start for the subscriber. So the key challenges and learnings in this process till now has been the fabric software interface that is between the MSS and the fabric layer. So the register interface needs to be highly optimized to accommodate such high rates of dBA cycles per second. So the integration has been ongoing for the VOLTHA, and the previous VOLTHA stacks have been on the x86 and ARM, and we have been porting it to RISC-V. So there have been multiple components which have been needing some patches and adaptation. There's some open source telecom frameworks which have been x86 or ARM first, like VOLTHA ONUs, Open Network Operating System. So we have been adapting that. And then certain debugging and profiling tools for RISC-V have been evolving. But I think we are going good there. So once this entire VOLTHA stack gets integrated, then the performance has to meet the goals that we discussed before. The future directions on this. So we want to evolve further into a complete cloud-based Kubernetes controlled solution. So the individual components of the VOLTHA are actually Kubernetes based. They are Dockers, and that eases the integration of the Kubernetes platform into the entire solution. We are evaluating further possibilities, and we have already figured out how to optimize the entire VOLTHA architecture. And we are seeing further possibilities of how we optimize the internal components of the GPON solution as well. We want to scale. We already have a prototype for XGS-PON as well, and we want to scale it to NG-PON2 on RISC-V. And we want to see XGS-V adaptation in the open telecom edge solutions. So the key takeaways are that RISC-V can support complex open source stacks. PolarFire SoC has become a proven platform for the telecom edge solutions like this. And the GPON solution is ready for real-world deployment, and it meets the reliability and efficiency standards. Here are some of the references. Whatever we discussed is all open source. So the hardware link and the RISC-V documentation and the GitHub, and GPON technology and VOLTHA.